Okay, it's great to be here, and I'm so glad that Harry organized this workshop because I think it's something that's really needed in the field, and I hope all the students here learn a lot today, and also especially the faculty. There's a lot to know about this field. So I'm going to talk about what are the supposed fundamental limits, and I have to tell you I'm kind of shocked at this particular graph. This is the size of the industry, and I remember when I left it about 25 years ago that the industry was very, very small and struggling, and it's quite amazing to look at where things are today. And in fact, I was in Germany 2 weeks ago, and they assured me that this was actually an underestimate of the production that's going to occur this year. They say in Germany alone they're expecting to install 6 or 7 gigawatts, which is a staggering number. When you consider that each of these watts is costing somewhere around $2, it means that the industry is of the order of a $20 billion industry, which means it begins to approach the size of other major electronic components like the size of the hard disk industry or the size of the DRAM industry and so forth. So it's gotten to be a very, very big industry, which is kind of fascinating. Yet most of it is actually still running on the same type of solar technology that was invented at Bell Labs in the early 1950s, which is a sort of conventionally designed silicon solar cell. So obviously we need to go beyond that. And speaking after me will be Dick Swanson of SunPower, used to be a professor at Stanford, and the authority who actually taught me whatever I know about solar cells. I actually learned from him. And his company, SunPower, I think is a leader in silicon photovoltaics in that the design of their silicon panel is completely different from the traditional design, and as a result the efficiency is much, much higher. And we'll get into what goes into the design shortly. First, I need to talk about things that are not science-oriented, but a little bit more economics-oriented. And this is kind of an unusual field. There are a lot of things you can do that are sort of mildly interesting, but they don't necessarily have an impact on the way this industry will evolve. And the biggest realm of controversy relies in the question, do you go for low efficiency but low cost, or do you go for high efficiency and high cost? And of course, unsaid is that, hey, what about high efficiency at low cost? That's also a possibility. But the controversy rages around the question of what is a reasonable efficiency target for a solar cell. And I have here a cost model, not my cost model, this came from Professor Barnett from the University of Delaware, but it shows, not surprisingly, that the efficiency ends up in the denominator of any cost model, okay, because the reciprocal of efficiency is what you get out of the panel. And so many of us believe that efficiency is extraordinarily important because the way to achieve low cost is to have high efficiency, because the output goes up and you're using the same amount of glass, the same amount of other resources, and yet you have more output, so that's got to be the lowest cost. Nonetheless, it remains a very controversial point, and to say that a lot of smart people disagree with me is sort of an understatement. In fact, the stock market disagrees with me. The stock market puts a higher valuation on a company like First Solar that is producing a 10% panel. It's putting the highest valuation on that company, which according to this graph is maybe doesn't have such a great future, because as efficiencies improve, then the costs will go down and they will find themselves stuck with maybe 3 times as much glass and 3 times as much everything costing 3 times as much. So that question remains somewhat controversial. Nonetheless, I will strongly argue that efficiency is indeed very important. And there are some lines here, some graphs showing efficiency, but basically the highest efficiency ends up being the lowest cost for the reason given. And this is the same graph. So how to achieve high efficiency? So this is a very complicated chart showing all the different demonstration modules. Many of them are just lab demonstrations with no hope of going beyond that. Let's try to just go back to fundamentals. And so this is what I regard as the fundamental way to understand a solar cell. And that is to think of it as a bucket. And you have raindrops falling into the bucket. And the raindrops, of course, are photons, and they're producing electron-hole pairs. And we're trying to build up as much water pressure in the bucket as possible, but there's leakage. There are recombination centers along the surface. So what you do is you coat the entire cell. If this was silicon, for example, you'd coat it with silicon dioxide. And that would eliminate most of the recombination centers on the surface. There are other leakage places to go, but you're actually trying to get work out of the bucket, so you're going to draw off some of the current as electricity, and so you'll have a balance between the raindrops coming in, the current coming out, and so that's sort of the name of the game. You just want to create a bucket for light and build up as high an electron hole density as possible, the electron hole density representing pressure. So this is one of the first things that Dick Swanson taught me. If you look at this particular design of the cell, you have here a selective contact for holes and a selective contact for electrons. Now, selective contacts are not that rare. It's hard to make an ohmic contact, and once you do make an ohmic, it's usually ohmic for one of the two carriers. So it's not that hard to make a selective contact. And if you look at this picture of the solar cell, it does not require a p-n junction. It came to pass after this famous paper by Schalk and Queeser that we're going to rely on heavily here. The people got to understand that the solar cell, yes, it can be interpreted as a p-n junction, but that is a very narrow interpretation. In fact, the equations, although they look like the IV curve of a p-n junction, are actually representative of a broad class of phenomena that don't involve p-n junctions, including especially photosynthesis. And so I'll get back to the photosynthesis in a minute. So you see, it's very general and is not. If you're a device modeler, well, we don't necessarily need device modeling. It should be more general than that. Okay. For example, okay, I got a few chuckles out of that. But hey, I challenge you as a device modeler, figure out how photosynthesis. Where's the device in photosynthesis? And obviously, you'll have to stretch, and we should all stretch that way. Now, the key feature is the selective contact. And I have here a picture of the ideal selective contact. So it would be a heterojunction. And in this heterojunction, let's say you want to pass electrons and you want to block holes. And so you just have a potential barrier, and you have a different kind of potential barrier. If you want to pass holes, it's like this. So if you have these types of selective contacts, your solar cell will work extraordinarily well. So what are the main things to know about solar cells? Well, obviously voltage, current, and fill factor. I'll talk mostly about voltage and current. So the first is what voltage to expect from a solar cell. It's sort of like free energy, and one of the things that we learn is that, let's say, population goes as the Boltzmann factor. So I can invert that, make that a free energy equation. I invert it, and this energy becomes free energy. It's kT log, and yes, I have a population. And if this was simply a molecule or a quantum dot, it would follow the Boltzmann statistics pretty well. And the free energy would be the excited state population in the light divided by the excited state population in the dark. And this is a very important point to make, is that even in the dark, at room temperature, completely unexcited, there is always some excited state population, even if there's nothing going on. And so it's the excess over that excited state population that gives you free energy. Now, those of you who are into semiconductors, the equation is very, very similar, except there's a 2 here. And I was puzzled. Why, for molecules, you don't have the 2? And so I remember at that time I was working at Exxon, and there was a very boring management meeting. And I was sitting in the back row. And sitting in the back row with me was Bob Schrieffer, who was the Nobel laureate who is provided the theory, the BCS theory for superconductivity. And he was a very highly paid consultant at Exxon. So he had to sit through the same stuff because they were paying him enough money, even though he was a Nobel laureate. And so without any warning, he was sitting next to me. I said, hey, what's this factor of 2 about? And I gave him no warning to think about this and come up with a considered answer. It took him about 10 seconds. And he said, oh, this factor of 2, this has to do with statistical mechanics. If you have molecules, the electron and hole have to sit together on the same molecule. But if you have a semiconductor, the electron and hole, they can go their separate ways and fill up the whole phase space of the semiconductor. And wow, that's it. That's why there's a factor of 2. It has to do with the phase space, the greater phase space. The density is really density squared. And so it shows that a Nobel laureate in theoretical physics does tend to be a very smart person. So he explained it. Now, how to think about voltage, though? So I gave you one way of thinking about voltage. I'll give you a second way to think about a voltage. However, you have to have learned some thermodynamics, which fewer and fewer students learn these days. So you have to know that free energy is U minus Ts. Now, surprisingly, this formula applies even at the level of individual photons. And so you could, certainly everyone knows h nu is the energy of a photon, but maybe you might be surprised that each photon actually carries some entropy associated with it. And if you've learned a little bit of statistical mechanics, then you know the entropy is k log W. So the formula for the free energy of a photon is h nu minus kt and log of the number of different configurations of the photon. Okay? And this is actually, although this is not normally taught, this is actually perfectly legitimate and gives you a warning, is if your photon has a great many configurations, much more than what you expect, it's going to be carrying a lot of entropy with it, and the free energy will be less than the photon energy. And indeed, this free energy is what determines the voltage. So what I'd like to do is to follow this formula and go to the operating point voltage, and it says h nu. Well, let's say all the electrons thermalize to the band gap, so I'm down at the band gap of the semiconductor, and I'm going to subtract off a bunch of entropy terms. And I think this is quite instructive. So first of all, what is the major entropy of photons? The major entropy is associated with the fact that when you look at the sun in the sky, it subtends a very small solid angle. And yet the solar cell doesn't, in most cases, does not use that information. In a concentrator cell, you do use that information a little bit to enable focusing. But to the extent that you have a device that cares not at all about the directionality of the incoming sun's rays, you have thrown away all that information. So that information represents quite a lot. It can be thought of as the randomization direction. So 4 pi steradians means the photons coming to you from any possible direction, and the actual solid angle subtended by the sun, it's about 1/100th of a radian, so you have to square it to get the solid angle. Ends up that this factor is close to 100,000, and when you take the natural log, it's about 12, and 12 times kT is about 0.3 of a volt. And of course, everything is like a little heat engine, so you have to take into effect that you're running at ambient temperatures, at room temperatures. Okay, so that is your actually biggest free energy loss, is the randomization of direction of the photons. Now you have a number of other losses. One of them has to do with the ability to trap the light internally in the solar cell, and I'll dwell on that at length. It's 4n squared, and that actually does contribute to the voltage in many types of solar cells. And if you don't take advantage of it, then you lose that roughly 1/10 of a volt there. Now, there's another reason why you have to lose a little bit of free energy, And it goes back to the picture I had of the solar cell. Why should the electrons and holes are kind of happy sitting inside the material? Why should they go into the wires? And you have to give them a reason to go into the wires. And in fact, the reason is, well, you have a lower voltage on the wires than what you build up at open circuit in the cell. And so you give the electrons and holes a strong reason to leave the cell and go into the wires. And a strong enough reason is just to give up a few kT of energy. And so these few kT, it ends up, this is the formula, you can work it out from the diode equation, and there again you lose about another tenth of a volt, giving the electrons and holes reason to go into the wires. Now, then there's yet another loss mechanism, and this has to do with the quantum efficiency of the material. And many materials, instead of the electrons and holes just sitting there, they recombine as heat. This makes it difficult to build up a high density of electrons and holes, and you lose voltage due to poor quantum efficiency. Now, let me tell you where I got this viewpoint. This viewpoint did not come from a solar cell expert per se. It came from a graduate student writing in his PhD thesis, a fellow who eventually became a biophysicist by the name of R.T. Ross. And he was working for Melvin Calvin at Berkeley, working out the science behind photosynthesis, and was very strongly influenced by Shockley and Queisser, and realized that the same thing applied in photosynthesis. And this was the picture that was put forward, and I strongly recommend this paper from 1967 that puts forward this way of looking at things. Now, so I'm coming to one of the major conclusions of my presentation, which is that you're going to be paying quite a price, and I'll give you an example. Suppose you you're asking what your operating point voltage is, and you start with a band gap of silicon. And suppose it had every kind of entropy I had on the previous slide. All of those entropy terms add up. You add a 0.3, 0.1, 0.1, 0.3. It adds up to 0.8 of a volt. And what it suggests is that the operating point, if you're doing that badly, the operating point voltage would be only 0.3 of a volt. And now, that's kind of sad. Only 0.3 of a volt from all those big photons. Some of them were 3-volt photons. It shows that you really have to do a good job on voltage. Yet voltage is the aspect that is most difficult to understand. Current collection maybe is a little bit easier to understand, but voltage, you have to have an appreciation for statistical mechanics, and sometimes the students don't get to take that course anymore. But there's another lesson here, is be very careful trying to play tricks with small bandgap photovoltaics, because you're on a very slippery slope. If things don't work out perfectly for you, you could do the subtraction and end up with virtually no voltage. And so there's a real danger of that. And you'll see examples where I believe people have fooled themselves, convinced themselves that, oh, I've got a great concept to do something with the infrared photons. I say, I'm sorry, those infrared photons, by the time you subtract off the entropy term, there's just not enough free energy to be worth it to do fancy things with the infrared photons. On the other hand, if you're talking about the blue and green and yellow photons, yes, those, then you start with a much bigger voltage, and even if you're not doing well, you still have a lot left over at the end. So that gives you an implication of what to do on the voltage. Try to do a decent job, especially on the big photons. Okay, now I'm going to switch over to current. The idea is very simple. You want to absorb the incoming light in as thin a layer as possible. If you really want a very thin layer, use a direct bandgap. For example, a direct bandgap like gallium arsenide absorbs about 10,000 times more than an indirect bandgap. Now, so I'm going to mention here the concept of light trapping and contrast two situations. One of them in which you make a single pass and you have one shot to absorb, and the other in which you make you trap the light. You have some texture on the surface. The light loses all memory of the angle at which it entered. It bounces back and forth inside and has a difficult time to escape, whereas a plain parallel solar cell is absolutely guaranteed to escape. And so you get a very big increase in the optical path length, huge, really. And you can make your solar cell way, way thinner. So I'd like to then bring up the point which will come up repeatedly. A good solar cell should be a good LED. In fact, the design considerations are roughly the same. That you go into the solar cell and you look for multiple passes. In the same way, in the LED industry, everybody in the industry now knows you have to texture to get the light out. And it's very similar. And if you fail to texture, only 2% of the light escapes, and then you've got to come up with a strategy how to get the rest of the light out. So that is kind of a big deal in LEDs. So how do you contrast these situations? So let me contrast them in the following way. And now I'm going back to your childhood. You teach a child about shapes, okay? And, well, I remember learning about shapes, but nobody told me that certain shapes were ergodic and certain shapes were non-ergodic. In fact, when I took a class on statistical mechanics, I was quite convinced after the class I would never, ever use the concept of ergodic in my career. And I could safely forget it. However, here's a case where you actually need the concept. Here are shapes. They're perfectly legitimate shapes. But the light rays do not get randomized internally. In fact, any light ray that is incident also escapes. And that applies to simple shapes like the sphere, the rectangle, the parallelogram, etc. Who knew that those shapes were drastically different from the ergodic shapes? And the ergodic shapes are the ones, if you follow the light ray, it quickly loses all memory of where it came from, and it fills the internal phase space. And the ellipse has that property, the trapezoid has that property, and what it means is that definition of ergodic, the time average motion of the light ray is the same as the phase space average, which is to say it fills up the entire internal phase space. And in these shapes, on the left side, the internal phase space is not filled. So obviously, we want to make our LEDs and our solar cells out of the ergodic shapes. There's another way to think about this is in terms of a density of optical modes. And if you look up the density of states, it has a refractive index in it. And there is so where did the 4n squared come from? There's a factor of 2 from double pass. And there's an additional factor of 2 that was first pointed out to me by Dick Swanson, is that you have to do cosine theta averaging. And you put all the factors together and you get 4n squared. Here's something that sometimes people get confused about, is they say, oh my God, you're using total internal reflection. Isn't that going to be completely messed up by your anti-reflection coating, which is required? And you have to think about this a little bit, but the two are totally consistent with one another. The anti-reflection coating corresponds only to those rays close to normal incidence that get in and have no effect at all on the fact that most of the rays are totally internally reflected. So these things are mutually compatible. That has also taken people a while to realize. Another thing you can sort of arrive at is that random roughness, some definition of random roughness, you do approach the statistical mechanical limit, and often people used to ask, and I actually came up when I was working at Exxon, people heard what I said about this light trapping, and they said, okay, I have a scheme to do better than that. And so there's always a hope that someone is going to do better than the 4n squared factor. And my answer to them was, if you succeed in doing better than that, then you will have a perpetual motion machine. Now that, of course, is the worst insult that you could give, and it was very effective. However, it's safe to say that nowadays many, many people are looking for ways to do better. And just keep in mind that the 4n squared factor only applies in geometrical optics. In wave optics, maybe we can do better. And there is a huge amount of research on that. And what should the pattern be? Should it be a photonic crystal? And I don't know. Okay, so that had to do with the current. And now here's an important point, is that the voltage, I talked about the operating voltage, and it's pretty simple. I showed you this formula earlier. You're losing kT log of this. This is to coax the electrons and holes out of the solar cell into the wires. And so this is pretty universal. So if we have a good idea of how to achieve a high open circuit voltage, we will also have a really good idea on what the operating point voltage is. It will just be reduced by kT log of of a moderate number. So it's enough to understand to try to achieve a high open circuit voltage. Let me sort of introduce the physics of a solar cell at the open circuit condition. And this, I would have to say, even though I've been in this field for a very long time, there are new things that I've learned recently. And this has to do with how an ideal solar cell works. And this is for an ideal material. So you'll see there's a rather special property. Suppose you bring light in and you create an electron-hole pair. And let's say that electron-hole pair recombines and gives you a light that then scatters around internally, finally getting reabsorbed, re-emitted, reabsorbed, re-emitted many, many times, and finally on one of those re-emission events escaping. So you might find this to be very strange. Most solar cells do not operate this way, but a very, very high efficiency solar cell will operate this way. And this represents some kind of very ideal solar cell, that there would be tremendous internal absorption, re-emission, etc. And for that reason, the very, very ideal solar cells don't need to have texturing to get the internal randomization. In fact, the absorption and re-emission process itself can provide some randomization. But it's very, very demanding as to the quality of the material, because there are so many absorption and re-emission events. Unless you have very close to 100% internal fluorescence yield, you will not contribute to the outgoing radiation. Now, why is it important to contribute to the outgoing radiation? At the ideal open circuit point, all the incoming photons come out as outgoing radiation. And that's the detailed balance limit. And that's what Shockley and Queeser told us about solar cells. That will give you the highest voltage. So it's not so much a device property, but really a thermodynamic property, a balance where you try to achieve the highest outgoing radiation. And you want to achieve that with the highest internal concentration of electrons and holes, which means you don't want to have any additional loss mechanisms that would prevent you from achieving the highest possible density. And so if you add a loss mechanism, that will cost you. You will not be able to build up as high a density. So we have to work to get the highest open circuit voltage. We have to work very hard to try to make the solar cell into a terrific LED. And so that's kind of interesting. And if we do that, we will actually increase. If we make an efficient LED with more outgoing radiation, the voltage will actually increase. And this is a little bit counterintuitive, because people say, oh my God, you're going to lose all your current as external fluorescence. Isn't that the dumbest thing you can imagine? But keep in mind, all we're trying to achieve is a good open circuit voltage. Okay? And once we have achieved a good open circuit voltage, we just subtract off a few kT, and all of that current, which would have gone out as fluorescence, useless, you go to the operating point, and it all ends up, sacrifice a few kT, and it all ends up in the wires. And so for that reason, it is not, it should be intuitive. It seems counterintuitive, make a good LED, but it should be somewhat intuitive that making a good LED, yes, at the open circuit point, you can always extract the current at the power point. So you are trying to achieve the highest open circuit voltage. So you have to make a good LED. And so this has taken people a little while to learn, because most solar cells don't perform that well, and they're not particularly good LEDs either. So what do we know about LEDs? Don't make them plane parallel. And the other thing we learn about LEDs, if you try to design LEDs for extraordinary efficiency, the internal losses get to be very serious. And so in LEDs, they're fighting the same issues we are in a solar cell. And to give you an idea, if you have a sort of a poor fluorescence yield, you'll end up the energy going away as heat, and that will reduce your external fluorescence yield. And what we're going to find, this is one of the main points I'm going to try to make, is you become very sensitive to the internal fluorescence yield because of the need to absorb and re-emit many times. Now, this idea of light trapping and absorption, re-emission, and randomization, this is actually implicit in the Shockley-Queisser analysis. They didn't particularly need to have texturing for the light trapping. They got it for free with the assuming perfect internal fluorescence yield. So you got randomization in direction that way. But it's there and it's implicit in the Shockley-Queisser limit. So the Shockley-Queisser limit gives you an efficiency of around 33.5% in a single band gap cell, and that's very ideal. But that's very ideal if you have a material with 100% internal fluorescence yield. Now, what if you don't? What if it's less than 100%? Well, there's a very severe penalty in terms of the voltage associated with the fact that if you have a slight drop-off from 100% to 90%, you get a very substantial loss in performance, and you drop significantly below the Shockley-Queisser, the ideal thermodynamic limit. And to show you that it all happens when you're very close to 100%, then you drop to 80%, and then you only lose a tiny amount. So almost all of the penalty occurs as you're just below 100%. And so this is sort of a, if you like, a little corollary to the Shockley-Queisser limit, is that, yes, you have to be ideal. In fact, you have to be really close to ideal. And a lot of it shows up right away in the open circuit voltage. And you lose a fixed amount. You lose of the order of, let's say, 70 to 100 millivolts, regardless, and this is like entropy loss, regardless of the photon energy. So up here with the big photons, 70 millivolts is nothing. But if you're talking about a small band gap device and you're going all the way to the operating point, yes, 70 or 100 millivolts can be pretty severe, very severe penalty. And so that's something to keep in mind. And if you go back to this, you see the biggest penalty is down here for the smaller band gaps. It's part of the warning. There's not as much free energy in the infrared photons, so they're much more vulnerable to anything not being ideal. And by ideal, it has to be 100%, or really, really close to that. And of course, that's quite rare, although it does come up. And to get another way of looking at it, if you're trying to get the light out and make a good LED, it could take as many as 125 absorption re-emission events. And so that's why you've got to have a tremendous internal fluorescence yield. And that sort of explains it. Another way of looking at it is if you look at the internal fluorescence yield and look at the ability to get light out, your LED, you lose a lot. As you drop below 100%, even to 95%, you're losing very quickly on external fluorescence yield. So they're brothers. The LED and the solar cell are brothers in this way. Now, most of the randomization comes from the internal fluorescence. You do get some if you do texture. So in this very ideal type of solar cell, the texturing helps, but not as much as it would in a more average type of solar cell. Why? Because most of the randomization is coming from these internal fluorescence events. So this is a picture that is often shown, and it gives an idea of what the main problem in solar cells is. It's the current and voltage, but it's also the fact that many of the infrared photons are sort of wasted. So all of these photons here are wasted, but I remind you, those are the ones that didn't have that much free energy anyway. But a lot of the big ones are also wasted out here. And so there's a very high priority in finding a way to deal with the multiple band gaps, and especially to get more power out of the high energy photons that do have a lot of free energy. So there have been a couple of proposals for doing this. One is to produce more than one electron hole pair per photon. I have picture a single photon producing large numbers of electron hole pairs. And the other approach, of course there are many others as well, but the main approach is to use multiple junctions and stack them up so that the big band gap skims the cream of the big photons, and then the small band gap takes the smaller photons, and so forth. Now, what about this photon down conversion? I call it photon down conversion. It could just be a big photon producing more than one electron hole pair. People have gotten very excited about this in recent years, and there's a paper in 2006 from NREL, and it projects that if you allow for this effect, you can end up getting efficiencies as high as 45%. So that's well above the normal limit of 33%. So this got people very, very excited, but you have to be a little bit suspicious. In order to create lots of electron hole pairs, you have to have a smaller band gap, and I caution you, smaller band gaps don't have as much free energy. And you see a lot of the benefit is toward the infrared. They have their optimum power point down around 0.7 of a volt band gap. That is dangerous. And if you think about it then, instead of assuming ideal perfection, as that paper did, let's just say that the internal fluorescence yield was 90%. It went from 100% to 90%. It's still a terrific material by most measures. Well, the effect is very, very devastating. The ideal efficiency goes down very rapidly. The infrared ones go down even more rapidly. And once again, we find a very severe drop between 100% and 90% internal fluorescence yield, and then a small drop down to 80%. So it gives you an idea that this is maybe a dangerous strategy. This is sort of very ideal, producing as many as 6 carriers per photon. Let's try to be reasonable, 2 carriers per photon. It's still a pretty severe loss. And if you're down at 90% quantum efficiency, boom, you're down here. You're practically the same as not producing multiple carriers. You're down around 33, 34%. So it shows that this idea of producing many carriers per photon, it does put a heavy burden on the quantum efficiency, the internal fluorescence yield, I should say. So let me summarize. I talked about light trapping and being ergodic and being textured and all that stuff. The implication is that you can make a much thinner solar cell and save semiconductor cost. Not that you'll get more current. You might get a little bit more current, but mostly it's about reducing the amount of material. But another thing to keep in mind, in ideal circumstances, you will pick up about 1/10 of a volt, which is sort of implicit in the already implicit in the Schottky-Queisner analysis. But what is the more far-reaching conclusions? I hope that you find it intuitive that external fluorescence is not a loss mechanism. It's actually a benefit. It is required for high performance. However, if you have in mind to approach the theoretical limits, you need to have an internal fluorescence yield well over 90%. Now, that's rare, but it comes up. And I did manage to get a paper published in Applied Physics Letter once. And I had, in the title of the paper, the referee accepted this, 99.7% internal fluorescence yield in gallium arsenide. So gallium arsenide is rather remarkable, but I'm sure there are other materials that are also very good that way. And if you depend very heavily on infrared photons, it may work in theory, but it's unlikely to be robust and may not fulfill the promise. So I would say, what are the main issues remaining in the photovoltaic field? We need more practical methods for spectral splitting to use some of those high-energy photons efficiently. And another issue that has not been worked out, we talked about the light trapping, but we honestly don't know how well the light trapping can work in the wave optics limit. We think it can work better than in geometrical optics, but I've seen some papers recently that suggest that indeed it can, and there are some pretty good ideas out there. But that remains to be worked out, is how well you can do with a very thin solar cell in the wave optics limit. So let me leave it at that, and I'll tell you, I'm looking forward to the other talks right after me.